Hey everybody, let's look at vectors in the plane. This will be in the last unit of your trig. A directed line segment PQ has initial point P and terminal point Q. Its length or magnitude, you'll hear that used interchangeably, is denoted by a double vertical bars around your directed line segment. And so it looks like double bars with PQ inside and can be found using the distance formula. Now, just as far as the vocab goes, the initial point, the terminal point, directed, it's actually called a ray in geometry. And the arrow above tells you the starting letter P, the ending letter Q. Two directed line segments that have the same magnitude and direction are called equivalent. The set of all directed line segments that are equivalent to the directed line segment PQ, is a vector V. And those vectors in the plane will be written as something like V, sometimes U, but anyway, it'll be a single letter representing a directed line segment. We're going to show that U and V are equivalent. Vector U starts at the origin and ends at 3, 2. Vector V starts at the point 1, 2 and ends at the point 4, 4. Now, as far as the same direction goes, you can calculate slope. Remember, y2 minus y1, that's 4 minus 2, that's 2. This 4 minus 1, x2 minus x1, 4 minus 1 is 3. So we have a slope of 2/3. Rise 2, run 3. You can also verify that with vector U. Rise 2, run 3. Same slope, same direction. So now we just need to make sure that the length of each one's the same. So when you get ready to calculate that, for vector U, that's this bottom one, we have x2 minus x1 squared plus y2 minus y1 squared. That's 9 plus 4, which is 13. And then we check vector V and get its magnitude. So we have square root of y2 minus y1, x2 minus x1. So you take the difference in your x's, square it, the difference in your y's, square it, add them together, and we get square root of 13. So these two vectors have the same slope and they have the same length or magnitude. The component form of the vector with initial point P and terminal point Q is given by these little less than and greater than symbols. They're called chevron. This is a chevron form. So basically, to get your x value, quote x value for the vector, it's q1 minus p1, so you subtract the x's. Then for the y coordinate, q2 minus p2. That difference will be the first value in your vector, and the second difference will be the second component. What a component form does is you take any vector, like the first two we looked at the bottom of the first slide where we had vectors U and V. Vector V, if you were to reset it using this formula, it would become vector U. The component form is the one that starts at the origin and maintains direction and length. The magnitude or length of a vector V is given by this formula, and we did that again on the first slide. It's x2 minus x1, basically. If you think of them in terms of x's and y's, x2 minus x1 squared plus y2 minus y1 squared. If you have your vector already written in component form, it's just the first value squared plus the second value squared. Square root the total, you get your length. If the length is equal to 1, then the vector is called a unit vector. So let's do an example. Find the component form and magnitude of vector v that has the initial point 4, -7 and terminal point -1, 5. If you want to pause the video and plot those 2 points, then come back on and we'll calculate the component form. Feel free to do that. Okay, so if you pause and you're back, we plot 4, -7. So that's going to be in quad 4. The terminal point -1, 5 would be in quad 2. So let me sketch that. This is going to be very basic. 4, -7, -1, 5. Be very careful with the direction. Now, if you were to calculate the difference in x's, to get from -1 to 4, you have to travel 5 units, specifically -5. So we have -1, -1 minus 4, that's -5, and then 5 minus -7, here it is written out, you get the vector -5, 12. Well, now, -5, 12 you don't see in this diagram down here, but that's what would happen is if you take the initial point, move it to the origin, and then draw your vector with the same length and direction, it would end at -5 and 12. So that's what the component form does. It gives you the ending location if you were to move your vector where it started at the origin. Using your distance formula, make the calculations. -5 squared is 25, 12 squared is 144. That gives you a total of 169, square root 13 units long. Okay, we're going to look at some operations with vector notation. Let vector v be -2, 5 and vector w be 3, 4. Scalar multiplication, 2 times v. It's exactly how you would think of it. It's 2 times the components of vector v, so that's -4, 10. Subtracting w minus v, subtract the same locations. 3 minus -2, that's 5. And then 4 minus 5 is -1. V plus 2 times w, I'm going to recopy vector v in its form, component form, and then 2 times w would give you the vector 6, 8. Add the like parts. -2 plus 6 is 4. 5 plus 8 is 13. So the operations of add, subtract, multiply, they're very intuitive. You would just do it like you normally would multiply, add, or subtract. Second example, let vector u be 1, 3 and vector v be -2, 5. The magnitude of twice the length of vector u can be calculated as 2 times the length of u in its original form. Alright, so for vector u, to get the distance, or length of it, we're going to do square root of 1 squared plus 3 squared. That's 1 plus 9 is 10, so 2 times square root of 10 is the length. With magnitude, you're allowed to pull the scalar or constant out. If the scalar happens to be negative, then you pull it out, but you take the absolute value of it to make it a +5. And the length of u is still the same. It's still square root of 10, but it just has a new multiplier. And again, that's because length is positive or 0. Can't have negative length for these. And then just for an extra example, the magnitude of 3 times v, we can calculate 3 times the length of v, so that's negative 2 squared plus 5 squared. That's 4 plus 25, which is 29, and we multiply it by 3. I do want to mention that a negative scalar with a vector, if we're not finding magnitude, maybe we're just doing negative 5 times u, a negative coefficient reverses the direction of a vector. So if you have a vector, call it u, that runs up and right, negative u will run down and left, totally opposite direction. Third example, find a unit vector in the direction of v, and then verify that it is a unit vector by checking that the magnitude is 1. Okay, the formula for finding a unit vector is the original vector over its magnitude. The magnitude of this one we've already calculated up here. Negative 2 squared plus 5 squared is 29. So magnitude of v is square root of 29 times each component of v. That gives us the unit vector negative 2 over square root of 29 and 5 over square root of 29. To check that this actually has a length of 1, you put these numbers through the magnitude, and we're going to say the first number squared plus the second number squared. That's going to be 4 over 29, 25 over 29. 29 over 29 is 1. Square root of 1 is 1. So we found the unit vector and verified it. If u is a unit vector such that theta is the angle measured counterclockwise from the positive x-axis, that's kind of a long way to say standard form, then your vector u will have an x and a y component, which can be also expressed as the cosine and sine values of the angle. There's also another form for vectors using I and j notation. The first entry of your vector will have an I, the second will have a j. The angle formed from the counterclockwise rotation is tangent inverse of the second number over the first number, y over x. All right, so let's just do an example. Find the direction angle of vector u, written as 3i plus 3j. What I like to do is convert I and j notation back to component form with the chevron. Okay, so x is 3, y is 3. The angle is going to be tan inverse of y over x. 3 over 3 is 1. And what's tan inverse of 1? 45 degrees. Very good. Here's the visual of that problem we just finished. If we take the vector 3i plus 3j, or in other words 3, 3, if we put the initial point at the origin, the terminal point at 3, 3, the angle formed between the positive x-axis and that vector is 45 degrees. Let's do one more example. Let's repeat for vector v, which is written as 3i minus 4j. If you write that in component form, it's 3 and negative 4. The angle will be tan inverse of y over x. Tan inverse of negative 4 over 3, using your calculator, make sure you're in degree mode too, you will get negative 53.13 degrees. Now from our trig inverse sections that we've done in the past, remember tan inverse, you're going to be finding an angle in these right two quadrants. Well, this negative 53.13 is represented here. Up here, remember, in the very top paragraph, the angle we're really after is the one measured from the positive x-axis counterclockwise. So we're actually looking for that angle from the positive x-axis all the way around to our vector. Well, how many degrees are in a full rotation? 360 degrees. Very good. So we take 360 degrees, remove that little part, and we get the angle that's marked in yellow here as 306.87 degrees. Please reach out by phone, email, office hours if you have any questions. I hope this video helps, and I will see you around.